Our next speaker is Dr. Michael Pavia. He has been in the biotech, pharmaceutical, and energy sector for more than 30 years. And Dr. Pavia serves as a Chief Technology Officer of ULT Recovery and its predecessor, Glory Energy, a company focused on using microbiology to increase oil production from existing wells. Previously, Dr. Pavia was entrepreneur in residence with the venture capital firm Oxford Bioscience Partners, focused on applying novel biology and chemistry to life science and energy solutions. Prior to joining Oxford, Dr. Pavia was Chief Technology Officer at Millennium Pharmaceuticals, where his major focus was to improve the productivity of the drug discovery and development processes through the appropriate use of new technologies. Vice President Cambridge Research at Sphinx Pharmaceuticals, a division of Eli Lilly & Co., focused on development of combinatorial chemistry technologies, and held senior scientific positions in the Department of Chemistry at the Parke-Davis Pharmaceutical Research Division of Warner Lambert with focus on CNS drug discovery. Dr. Pavia holds a bachelor's degree in chemistry from Lehigh University and a PhD in organic chemistry from the University of Pennsylvania. Thank you very much, Dr. Pavia, for being with us today in our meeting. Thank you very much.
Well, thank you very much for the invitation to speak today and for your kind introduction. So I'm Michael Pavia, Chief Technology Officer of ULT Recovery, a company based in Houston, Texas. Today, I would like to tell you about a breakthrough technology to enhance oil recovery in both conventional reservoirs undergoing water flooding, as well as unconventional reservoirs that have been fractured and are now exhibiting significant decline. The title of my talk will be Novel Biological EOR Processes for Improved Recovery in Conventional and Unconventional Resources. The outline for this presentation is for both the conventional and unconventional reservoirs. I will describe to you how the technology works, show you lab evidence supporting our mechanistic hypotheses, and then show you our successful field results. For the unconventional approach, I will also describe efforts to further optimize our initial positive results. So our company vision has always been tomorrow's oil from yesterday's well. And what do we mean by that? Well, we know where the oil is. You've already drilled the wells and you've already spent the money to drill the wells. So wouldn't it be great if we could maximize your existing return on investment? This is the driving vision behind the development of our technology. What we've shown so far is the technology is applicable to both unconventional and conventional reservoirs. It is a very low-cost production enhancement technology. For conventional reservoirs, we've seen 9 to 12% incremental recovery. For unconventional oil wells, we've seen a greater than 10% EOR increase for fractured wells. In the conventional examples, we've shown lower water lifting costs. For both technologies, we get a very quick production increase response. The minimized surface facility investments. So the capital expenditure required is very low compared to other technologies, and the operating expenses are also very low. And finally, the technology is safe, it's simple, and it's environmentally friendly. So I'll begin with our work in conventional reservoirs undergoing water flooding. Our technology now has been deployed in more than 15 conventional oil fields in the US and Canada, and has demonstrated greater than 12% increase in incremental oil recovery. Okay, so now how does the technology work? It all starts with the microbes, and these are microbes that are already present in the reservoir. For the most part, these microbes are dormant, they're not growing. And they're not growing because they lack the essential nutrients required for growth. So what we do is we go into the field and we obtain samples of the oil in the water from your field. We then return these samples to our laboratory in Houston, where we determine which combination of proprietary nutrients will activate the existing microbes to do what we want. And what do we want them to do? So we want them to grow and multiply, but we want a dynamic growth, which I'll show you in just a minute. What happens here is this results in an improved sweep efficiency and production of surfactants on the microbe surface, which results in a reduction of interfacial tension. So let me show you how this works on this slide. So if you look at the left part of the slide, you'll see in light brown, rock grain. You see in black, the oil trapped in pores. You have a water flow pathway shown in blue. And in yellow are the microbes. Now, these microbes, they need a food source. So we would like them to eat a tiny bit of the oil that's in the reservoir. So these microbes start to eat the oil on the reservoir, and they grow, and they grow. And you move to the next panel, the second one from the left. The microbes keep on growing, and eventually they grow so much that they block the existing water flow pathway. When this happens, the water pressure from the existing water flow pushes the oil that's blocked out into the production stream. Now, if we go to the third panel, what happens now is the microbes don't have any more food. So they do one of two things. They either move to a different block pore so they can find more oil to eat, or they die and different microbes find the new blocked oil. And this just keeps happening over and over and over again. And this is what I mean by a dynamic process. The microbes grow, they open new water flow channels, they remove trapped oil, and this process repeats over and over again. So it's repeated in the reservoir until effectively the reservoir is cleaned of unswept oil. Now, this is an interesting slide. We've also shown this technology in the laboratory. So on the upper left, we show microbes growing and multiplying. Underneath that is the same diagram I showed you on the previous slide. So remember, the microbes grow, they block the open water channel, and this pushes out the trapped oil. So what we did in the laboratory on the right part of this slide is we set up a microfluidic chip device. So this is simply small pores etched into silicon wafers. And what we did was we modeled a bifurcated blocked oil channel. So what you see here is we grew our microbes by addition of our nutrients, and eventually these microbes blocked the injected water pathway and pushed out the oil. And I'm going to show you in a very quick video that this actually happens in the laboratory. That is actual trapped oil getting pushed out because of the microbial growth. Okay, so how do we apply this technology? So what you're seeing on the left, this is your existing water flood structure. You have your injection well where you're pumping in water. You have your existing water pathways, you have your trapped oil, and you have your producer wells. So what do we do when we apply our technology? It's in the red box on the right part of the screen. We go to the field with our custom nutrient mixture that we've designed in the lab. This is usually in a nutrient storage tank, say maybe 5,000 gallon storage tank with a pump. And we simply pump these nutrients, a very dilute concentration of nutrients, into your existing water flood operation. And then this does what I told you on the previous slide. It makes the dynamic biomass growth, it frees up trapped oil, and this trapped oil comes out in your producing well. So there's a few things that are worth pointing out here. Is what is required from surface structure to do this is to simply bring a nutrient tank and a pump and put it into your existing water flood operation. So a very inexpensive capital expenditure. The nutrients themselves are pumped in at very low concentrations, usually in the range of about 100 parts per million. So the operating expense of doing this technology is also quite inexpensive. The time to response that we've seen is from beginning of injection of nutrients to increased oil production is usually about 6 to 8 weeks. Now, this is a very busy slide, but I only want to make a few key points. So this is summary results from successful projects that we carried out in the US and Canada, California, Kansas, and as well as a project that we carried out in Canada. So I'll make a few points on the Kansas and California project, and then I'll show you more details on the Canadian project on the next few slides. But let me mention that all of these results have previously been published. So the Kansas project first. This was completed and published with Merit Energy. As you will see on the far right, the project at the top far right graph, the project was 4 years in duration, and it produced a projected 250,000 incremental barrels of oil. On the right graph again at the top, you can see the pre-technology decline curve. That's shown in blue and black, going from top to bottom. And you can see once we applied the technology at month 0, you saw a very quick, in about 2 months, shift of the decline curve to a post-treatment decline curve. So that's how we calculate the incremental barrels of oil produced. It's also worth mentioning that for this project, we turned the nutrients on and off several times in specific wells as part of this project. And the very interesting thing is, if you turn the nutrients off, the oil production returns right back to its original decline curve. Then if you start adding nutrients again, it shifts back to the enhanced oil recovery. And you can repeat that. We've repeated it several times in this case to show that effect. So that's really conclusive evidence that the nutrients are responsible for the enhanced oil recovery project. Okay, now let's move to the California project. What I want to point out here in particular are 2 effects that we saw. We predicted before we started the project by the theory of how this technology works, that up-dip producer wells from the injector would show a good effect, and we expected that down-dip producers would not show a good effect. And this is exactly what happened. You can see that on the second graph from the right. So that was pretty exciting. It did exactly what we had expected. The second thing I show you here is this is the turning on and off of the nutrients. That's the graph on the far right in the middle of the screen. And when you turn off nutrients, and then we actually also added oxygen to kill the microbes, you get oil production right back down to the level of before treatment. So for the Canada project, I'd like to show you these results on the next 2 slides. For this project, this was done in Alberta, Canada, and this was done in collaboration with Synovus, and it was carried on for nearly 2 years. The conclusions I would tell you here is we were able to show a 400% increase in oil production. We also reduced the lift operating expense by 50%, which I'll show you more about that on the next slide. This project we also were able to increase the oil cut as well. The reason for the reduction in the lift operating expenses is because we were achieving more oil with the same amount of water pumped in the water flood. And of course, the major expense in any water flood is the energy cost of moving the water. This result we published in JPT, Journal of Petroleum Technology, in March of 2015. This slide shows you that effect that I mentioned about achieving more oil with the same amount of water. So this was 2 wells that we did it in. You see the same result in both. But what you'll see here is upon implementation of our technology, the water-oil ratio, which had of course been previously increasing, shown in blue, became flat. So what that means is we were getting more oil with moving less water per barrel of oil. And the same result was seen with the second well. So this translates into a 50% reduction in lift operating costs. So that's a summary of what we've seen in conventional reservoirs undergoing water flooding. As I mentioned, we've now done over 15 projects, US and Canada, and several other parts of the world. So now I'll turn to our work in unconventional reservoirs. These are reservoirs that had been previously fractured and are now exhibiting the significant decline that you would expect. So first, I'll describe to you our theory of how this technology works. Then I'll show you some laboratory evidence to support our theory. I'll show you how we design and carry out our field implementations and the results from 2 field pilot projects that we carried out in the Permian Basin in Texas. Okay, so what are the technology advantages of this unconventional approach? So again, this is a novel biological enhanced oil recovery technology to be applied to liquid-rich unconventional reservoirs. It's environmentally friendly. We only inject biodegradable inorganic nutrients. We see a very quick response. You'll see that on the specific examples to come. And we see a lasting impact. We've demonstrated an increase in EOR by over 10%, and it's very cost effective. We think this has got the best rate of return of any commercial EOR approach for unconventionals, with the cost of incremental oil being less than $5 a barrel. Okay, so this slide I'll do quickly because I think everyone is painfully aware of this. Top 3 challenges with unconventional resources. You get overall extremely low EOR. Secondly, you get very rapid declines. So you fracture the well, you get a good production, and this declines very quickly over a period of time. And third, if you want to get more oil out of these wells, the costs of recompletion or existing technologies for enhanced oil recovery are not only are they very expensive, but they also run the risk of killing your producing wells. Okay, so why are we seeing rapid decline rate and low EOR? So as you know, hydraulic fracturing employs fracturing fluids mixed with various chemicals used to increase the viscosity of the fracturing fluids, reduce the friction, and increase emulsification. The percentages of these chemicals typically used in frac jobs can be seen in the upper left. So today I'm going to focus primarily on friction reducers, but gelants pose a similar problem and a similar opportunity using our technology. So we believe that the loss of fracture conductivity can be attributed to 2 major components. One is residual fracturing gels and flocculated friction reducers. In the middle of this slide on the left, it's well known that for friction reducers, when you expose these to calcium or iron, you form aggregates. This is shown in cartoon form, but it's actually shown at the bottom left of this slide in a real example. And what you get is these aggregates, and these aggregates cause formation damage. And this formation damage, that of course impairs the fracture network conductivity. And you can actually see that on the upper part of the left part, right part of this slide. So this blocks the flow paths of the reservoir fluids. Now, 2 of the main chemicals that are used are guar gum and polyacrylamide, also called PAM. So residual guar and PAM, they're both known to block fractures and pores, which subsequently affect the production rates. And in addition to that, high volumes of water and additives used in fracturing treatments and loss of the pay zones may also contaminate the pores, the fracture surfaces, and the networks. So we think this is the problem that exists. You can also see this in the laboratory. Here's examples of, at the top left, of looking at scanning electron microscopy. So you can see here the sample before absorption of these chemicals, samples after absorption, and it's clear that these pores are getting pretty plugged. On the bottom left, you see the same thing using nuclear magnetic resonance spectroscopy. So this is clearly a permanent permeability loss caused by chemical blockage on the fracture surface. Okay, so how does our technology work? So I'm going to spend a minute on this slide. It's a microbial technology or a biological solution. As I said earlier, it utilizes microbes that are naturally occurring in your reservoir. Now, here in the triangle are the 3 critical components for this technology to work. You have microbes, you have carbon, and you have nutrients. So, okay, what can I say about this? So microbes, they're present in your reservoir. They're there, but they're not doing anything because they're dormant. And they're dormant in the water phase because they lack essential nutrients. Okay, the carbon, this represents the food source. Now, this food source can be oil, as I showed you in the conventional examples. It could also be fracturing chemicals, which we believe is what's happening in the case of the unconventionals. So the microbes are there. They have the food source. They're lacking the nutrients. These are mostly gone from your reservoir, And what we do is when all three are present, we can get growth. And if you take any away, no growth. So we go in and we design a custom nutrient package to allow the microbes to become active. I should also point out something that I think is quite interesting. So the microbes, I said, are present in the water phase. The food is present in the oil phase, which is not miscible with the water phase. So in order for the microbes to eat, they have to get the food out of the oil phase. What we believe they do is they actually express surfactant molecules on the microbial surface. So the simple way to think about this is they're almost like small hands that reach out into the oil phase and pull food into the water phase. So they do this in order to eat, but what's great for us is when they do this, it causes a surfactant effect, which changes the interfacial tension. And this surfactants on the microbial surface reduces the interfacial tension and helps also mobilize residual oil. Okay, so the technology process of how we actually carry this out. This applies to both unconventional and conventional projects. But a key difference, which you'll see in a moment when I show you the unconventional results, is that conventional reservoirs require continuous injection of low concentration of nutrients for the life of the project. Our unconventional results required only a single nutrient treatment. Okay, so what do? When we find an operator who wants to apply this technology, we get the data that they have available on the field, and then we go through an integrated subsurface analysis using our scientists. Then we go to the field and we take samples of the oil and water from the field. We return these samples back to our lab in Houston. We do extensive lab testing. So we, of course, want to demonstrate which mixture of nutrients give the best growth of microbes, but we also want to see which mixture of nutrients give the best effect on changing the interfacial tension. So once we design our tailored formula for your specific field, we'll take it to the field and implement it. So as shown on the bottom here, we take our nutrient tank out, put it into the existing water flood, or in the case of unconventionals, get a pumping truck to pump the nutrients in one slug into the reservoir. We then resume production, we monitor. We can go back and optimize formulas and operation procedures if it's not optimal in your field. And then we ultimately get enhanced oil recovery. So next, I'm going to show you the results from our unconventional field pilot projects. So one project was performed on a previously fractured vertical well in the Midland Basin, specifically in the Sprayberry and Wolfcamp A formations. And the second project was performed on a previously fractured horizontal well in the Delaware Basin, but also in the Wolfcamp A formation. And it should be noted that both of these two pilot projects, when they were fractured, had been exposed to both guar and PAM. Okay, so here's project one. So project one was the fractured vertical well. What we did is we went in and we injected 500 barrels of a dilute nutrient solution. We did this just once and it took only a few hours. We then shut the well in for 7 days before resuming production. So what you see here on these two graphs, on the left is the monthly liquid production, and on the right is the daily oil production. So let's start on the left. What we saw immediately upon treatment, and treatment is that red T with the yellow around it, we saw a very fast increase in liquids of 85% increase. We monitored production for 6 months, and what you can see on the right part of the slide, the daily oil production, is we saw a 12% increase in EOR, but over the period of this experiment, we showed over 2,200 incremental barrels of oil added to the EOR. So what surprised me here was that we did one single injection of dilute nutrients, 500 barrels. We saw the effect that we saw, and the effect lasted for six months. And in fact, the company that did this only monitored it for 6 months. So I think a pretty exciting result. So pilot two is the fractured horizontal well. Again, we injected only 500 barrels of dilute nutrient solution, again, a shut-in for 7 days. What we saw here, and this is the same two graphs that I showed you in the previous slide. What we saw was, again, a 70% average increase in liquid production. The production, again, was monitored for 6 months. Based on the results here, we can extrapolate to an 18,000 barrel EOR. And again, I find this quite remarkable that it was only a single 500 barrel nutrient treatment. And as you might expect, we believe that the water with the nutrient is likely to enter into some limited fractures and probably those that are very, very near the wellbore. So this was not by any means an optimized treatment paradigm. So those are the results from the two pilots. What do we want to do next? We want to run full-scale projects in unconventional reservoirs, and we want to vary we want to change some variables to optimize them. We want to look at injection volume, nutrient concentration, injection frequency, and we want to do some zonal isolation or diverting and targeting. As I mentioned, with these horizontal wells, we want to add chemical diverters so that we can optimize the distribution of the nutrients throughout the reservoir rather than just have them go into the nearest fracture. In the laboratory, we want to carry out some fundamental research to improve our field successes. One of the things, I won't mention them all, but one of the things I'm particularly excited about is we're designing microfluidic chips that can be designed and then fabricated based on field porosity and permeability data. They can essentially mimic the rock in a specific reservoir. So we could design specific patterns to simulate the matrix fracture structures in the reservoir. We can create block channels in the microfluidic chips to simulate residual oil. And then we do microbial treatment with nutrients. And images that will be captured over time can analyze the recovery of oil and the change in oil distribution. So these are things that we haven't done yet, but we want to do with partners as we move forward to optimize the conventional treatment. So quickly, I'll show you a couple of laboratory results that support our hypothesis of biodegradation of polyacrylamide, guar, and another chemical frequently used xanthan. So what we did here is we measured UV transmittance. So of course, all of these chemicals are polymers, and you might expect that UV transmittance would be low because the UV doesn't get through because the polymers are not in solution. So what you're seeing at the bottom of the slide where it says no nutrients and no indigenous microbes, this is basically the control experiment. This is clean water, and that's the base level of transmission you would get. Now, with nutrients only, that's the formation water, which has circulating indigenous microbes in the water. And what you're seeing there on the left is that when we add our nutrients, we get an increase in transmittance, which would be in agreement with dissolution or digestion of the polymers into solution. Now you'll see also the line that says nutrients and indigenous microbes. This is if you let the nutrients grow the microbes over some time, you get a further enhanced effect. So we saw that with PAN, we saw that with xanthan, and we saw that with guar. And I won't go into the details here, but I think based on these results, probably the easiest to digest is probably guar. Okay, we also showed on this slide biodegradation of the fracturing fluid additives just in bottles with our proprietary nutrients. So we can actually see the visual change where the solution gets lighter based on addition of our nutrients. And what we want to do here is additional laboratory research to confirm and optimize our discovery to increase the performance in our commercial application. So we want to look at oil-water emulsion degradation. We want to look at wettability alteration. What happens there is when you continuously have this EOR treatment, a biofilm forms on the rock surfaces in the near wellbore area, which can cause alteration of wettability. We want to show that. We want to build numerical simulation models where we can estimate EOR enhancement and optimize treatment. We're also going to develop physical models where we'll study the buildup and the biodegradation of the hydraulic fracturing fluid components. So these are some of the things that we want to do in the immediate future. So finally, let me just give you a quick comparison to how this technology compares to another recommended EOR method in unconventionals, which is gas huff and puff. And what I won't focus on everything here, but I think production downtime is one that we should look at. So production downtime for gas off and puff is 3 months. For our technology, it's 1 to 2 weeks. The cost at the bottom of the slide, it's about $1 million for a gas off and puff EOR treatment. For our technology, depending on the well, it's between $30,000 and $100,000. And what this translates to is a payout period for gas off and puff of 9 to 12 months, and for our technology, 2 to 4 months. And quickly comparing our technology to drilling and fracturing, just go right to the bottom of the slide. The cost per flowing barrel for our EOR technology is less than 10% of the cost for drilling and completion. So in conclusion, that's an overview of our company's capabilities. As I mentioned, it's applicable for both unconventional and conventional reservoirs. It's a very low cost enhancement technique that gives very good results. You get a quick production increase. It's a low cost capital expenditure, low cost operating expenditure, and it's a safe, simple, and environmentally friendly technology. So we're pretty excited what this technology can do for recovering the significant amount of unrecoverable oil in both conventional and unconventional reservoirs. And we will be delighted to discuss how we can help your companies take advantage of this breakthrough. And finally, there's my contact information, and I look forward to hearing from you and look forward to answering any questions on the panel discussion. Thank you.